Hello and welcome. So today we've got the last chemistry session of BIOB. So after this session we then move on to organic chemistry and then into macromolecules and metabolism. So this section of the course was consisting of 6 lectures and this is the last of the 6 lectures. So as you all know, I'm Dr. Daniel Andrews and I'll be taking you through the lecture today. So as always, we've got our concepts that we need to focus on. So today we're looking at acids and bases. So we're going to be looking at the way acids and bases behave in the presence of each other in something called an acid-base reaction. So essentially acid-base reactions are all about a component called H+. So whether the acid or the base accepts or donates this H+, basically determines how it's behaving in the chemical reaction. So we'll see that the acids are the ones that have a H+ to give away, so they're the donators, whereas the bases are actually the components that are going to accept H+. So we'll also have a look at some other characteristics of acids and bases, the fact that they can actually be strong or weak, and what this means in terms of their ability to perform a chemical reaction. We'll also look at the biological importance of acid-base reactions, and one of the importance of these is the fact that we have buffers in the body which can actually help prevent our blood or other fluids from coming too acidic or too basic. So essentially the role of the blood is to limit the amount of pH change, which is basically the measure of how acidic or basic the blood is. So the first section we're just going to be focusing on what an acid and a base actually are and how they behave together in an acid-base reaction. From there we'll move into looking at what makes an acid strong or weak, and then the last section we'll look at how we can describe the acidity or how basic a solution is on a pH scale. And then we'll look at the buffer and how it plays a vital role in maintaining the pH of the blood to allow oxygen transport to remain intact. Alright, so some definitions to start with. So we know, hopefully, that acids and bases react together in a chemical reaction. So we're going to be exploring this in a fair bit of detail today. So when you have one reactant being the acid and one being the base, that is where they're going to react together via what we call an acid-base reaction. So you'll see this term a lot throughout the lecture today, acid-base reaction. So it just means one of the reactants is the acid and one is the base. And the hallmark of an acid-base reaction is actually the movement of this component that it's got a few different names, but most of the time we'll just call it H+. We'll see that H+ is just a proton. So we can actually determine which component of the reaction is the acid and which one is the base by how it is behaving in relation to the H+. So we'll see that the bases are the H+ receivers and the acids are the H+ donors. So what is H+? So when we see H, we know that that means hydrogen, right? So in earlier lectures where we've been looking at atoms, here's our hydrogen atom. So if you look at the periodic table, the hydrogen has an atomic number of 1, therefore it has 1 proton. So all atoms have to have an equal number of positive and negative charges, so because it has the 1 proton, it also means it has 1 electron. However, let's compare the hydrogen atom to H+. So hydrogen, when it's in this H+ form, in red, only has a proton. It no longer has an electron. So it's actually given away its electron to become this positively charged version of hydrogen, which is now an ion. So when we see H+, what you've really got there is a hydrogen atom that's lost its electron. So we'll call this either H+ in the session, or it can also be called a proton, because it's an atom that has lost an electron and therefore only has a proton. So hydrogen has no neutrons. So technically, H plus is just one single subatomic particle, and that subatomic particle is the proton. So it's important that we realize that acid and base reactions involve the movement of this H plus ion rather than a hydrogen atom. The reactions that move hydrogen atoms are the redox reactions. So we saw those in an earlier session. Today we're focusing on the movement of H plus, not the hydrogen atom. So here we can see how the hydrogen atom becomes the hydrogen ion. So it's the same process as would happen when a component is undergoing an ionic bond. An electron is being given away to another component. In this representation, we can see that the hydrogen atom is losing the one electron. So you can imagine that electron could be accepted by another component, or it may just be jettisoned and being released. So the important part of what we've got on this slide is the fact that once the hydrogen atom loses that electron, it now has one positive charge and no negative charges. And that's what we have for the hydrogen ion. And we can summarize that as being H plus. Okay. So it's incorrect to say that an acid-base reaction is the loss or gain of hydrogen. Technically, it's the loss or gain of H plus, which you can also call a proton. So as I said earlier, the acid-base reactions that we're going to be looking at today involve different compounds accepting and donating this H plus component. Alright, so what about an acid? What does it do in an acid-base reaction? So acids are the components that are actually capable of donating an H plus. So they can actually donate their H plus to a second compound, and the compound that the H plus is donated to is called a base. So essentially, the acid is giving away its H plus to a base. For a compound to be an acid, therefore, it actually has to have an H plus that it can get rid of. Okay, so it has to have that H plus, otherwise it can't actually have anything to give away. Acids can have more than one H plus to donate. However, each acid-base reaction only allows one H plus to be donated. So what this means is that in a single acid-base reaction, only one H plus can be donated. Okay, so for example, if the acid had 3 H plus that could potentially be given away to base compounds, how many acid-base reactions would we need to give away all 3 of those H plus? You'd need to do 3 separate acid-base reactions. So the first acid-base reaction would give away 1 H plus, the second would give away another, and the third will give away the last of the 3 H plus. So essentially, to give away all 3 of those H plus, we need 3 separate acid-base reactions. Another important characteristic of what happens to an acid in an acid-base reaction is once it actually gives away an H plus, it actually becomes a component that we call a conjugate base. So essentially, once the acid has given away its H plus, it's no longer the same compound, which we'll investigate in when we start looking at the acid-base reactions. But essentially, after the acid gives away its H plus, that now means that it's changed, and we can call the product version of the acid the conjugate base. Because it's lost an H plus in the process of the reaction, in theory it has the capacity to now take on that H plus again in a different reaction. That's why it's displaying characteristics that we can associate with a base. So the base is the other half of what we need in a acid-base reaction. So we can define a base as a compound capable of accepting H plus from a second compound, and that second compound is the acid. So essentially what's happening in an acid-base reaction is we've got the 2 reactants. One is going to be an acid and one is going to be a base, and the H plus will actually be moved off the acid and moved onto the base. So it's similar to what we saw in the redox reactions, where we had one component being oxidized and one being reduced. In that case, the hydrogen was being moved off the oxidized component and moved on to the reduced component. In this case, the movement is from the acid to the base, and what's being moved is the H+ ion. So what does a compound need to do to be a base? Essentially, it has to be capable of taking on an additional H+. So it has to be able to accommodate an extra H+ within its structure. And just like the acids, some bases can actually do this more than once. So some bases have the capacity to accept more than one H+. But each time it's accepting an H+ requires one single acid-base reaction. So for example, if the base was capable of accepting 2 H+, how many acid-base reactions would the base have to go through to get an additional 2 H+? Well, because we see this rule here that the base can only accept 1 H+ in a single reaction, that means there would actually be 2 acid-base reactions required for the base to take on those extra 2 H+. And just like the acid, the base will actually change in the course of the acid-base reaction. So once it's formed the product after accepting the H+, we now call that product a conjugate acid because it's taken on an additional H+. So we'll explore this idea of conjugate acids and bases more in later slides. Don't worry too much if you didn't get exactly what that meant yet. Key takeaway from these last two slides is the difference between an acid and a base. So that's the definition here. So the definition for a base is the H+ acceptor, and the definition for the acid is the H+ donor. So you can see in this little illustration here that you can't have one without the other. So you need the acidic component, which will donate the H+ to the basic component. And we've also seen, according to these last two slides, that each acid-base reaction involves the movement of one H+. So if there's more than one H+ that requires to be moved, then you need to do this in separate acid-base reactions. Alright, so let's now investigate the behavior of an acid during the acid-base reaction a little bit further. So we can describe an acidic compound as one that is a proton donor. So it has that H+ that it's willing to give away in an acid-base reaction. Remember, a proton is an H+. You can use these terms interchangeable. So in the acid-base reaction, the acid reactant that has the H+ will donate that H+ to a base. And by doing that, the reactant acid actually becomes a product that now has less H+. And we say that that now is the conjugate base because it's no longer an acid. So let's investigate these 2 points by looking at this acid-base reaction down the bottom here. So clearly states here that HCl is the acid. So you can see that the acid is reacting with a base, and in this case, water is behaving like a base. Water is not always a base, but in this reaction, it is. Okay, so what is the characteristic of our HCl acid here? What is it actually going to do in the course of the reaction? Well, because it's an acid, as the description says here, it's going to donate H+. So where is the H+ going to go? It's going to come off the acid reactant component and be accepted by the base. So you can see here that H2O will actually be accepting that H+ from the HCl, and that's going to mean that the H2O is behaving like a base. So once we've had this switching of the H+ by taking the H+ off the acid and moving it onto the base, the end result is that we've now got 2 new compounds, and both of these compounds have changed. So why is it that the product compounds are different from the reactant compounds? Basically, it's because the H+ has moved position. So it's been taken off the HCl and moved onto the H2O. So that now means that the conjugate acid has one extra H+ than it did initially. So initially it was H2O, now it's got one extra H+ and it's become H3O plus. And the other component, which was HCl, has actually lost H plus. So you can see without the H plus now, we've got Cl minus. So you can actually match up the pairs that match what the reactant turns into on the product side. So, for example, the first pair would be HCl, and then it turns into Cl minus. So that's one pair. And then the second pair is H2O and H3O plus. Notice that the first pair here, the only difference between these two is one H plus. So HCl contains one more H plus than the Cl minus does. Just like between H2O and H3O plus. The only difference between these two is H plus. So essentially that tells you that the reactant is turned into the product by the change in H plus. So what does the acid become once the reaction occurs? So you can see that after the reaction occurs, HCl has now lost its H plus and has become Cl minus. So we call this the product. So this is the product version of the acid, which is called the conjugate base. So why is it called a base? Because in theory, Cl minus could actually function to act like a base by accepting H plus in a different reaction. We now can see here that Cl minus doesn't have the capacity to give away any more H plus. Why can't Cl minus give away any more H plus? Because it doesn't have any. Remember, a component can only act like an acid if it has an H plus to give away. So that's why we call this one the conjugate base. So you can see that the acid will turn into the conjugate base through the process of the acid-base reaction. What about the base? Well, the base will actually turn into the conjugate acid through the process of the acid-base reaction. So the base functions as a base does to accept H+, and as it does that, it becomes a component with an extra H+. What do we know about components with extra H pluses? Well, in theory, they can actually give that H+ away and function as an acid. So this is the reason why the base turns into what we call the conjugate acid, or the product acid. It's because the base has now adopted a form where it has an extra H+, and therefore in a different reaction it could give away that H+. So no matter which acid-base reaction you look at, it always follows this same pattern. The acid turning into the conjugate base, and the base turning into the conjugate acid. So when you look at these acid-base reactions, try and find which two components match together. So there's going to be one reactant and one product that match together, and there will also be another pair of reactants and products. And from there you can actually work out how the reaction's taken place in terms of movement of H+, and that will allow you to work out which one's the acid and which one's the base. We'll practice this a little bit later on. So let's focus now on the base and how it behaves. So the base is the part of the reaction that is the proton acceptor. So in this case, it's H2O that's being the proton acceptor. So as a reactant, the base has the capability to accept H+, and it does that by accepting the H+ from the acid, which is HCl in this case. However, once the base has done that accepting, it now turns into the conjugate acid. So why do we call the product version of the base the conjugate acid? Because after accepting that H+, it's now got an extra H+, which could in theory be given away in another acid-base reaction. So you can see from these last two slides that there's some key characteristics of the acids and bases that we need to be aware of. Again, the acid is the proton donor, whereas the base is the proton acceptor. But we've also seen that the identity of the acid and base actually will change once the reaction has taken place. So the acid actually becomes the conjugate base, capable of behaving like a base in another acid-base reaction, and the base actually becomes a conjugate acid. And that conjugate acid, in theory, is able to behave as an acid in a different acid-base reaction.